Hello everyone. Salut. We're going to talk about trigonometric integrals. So let me just be clear. In this chapter, there's only two advanced technique of integration, substitution and by parts. Everything else, so trigonometric integrals in this section, trigonometric substitution in the next section, or partial fractions in the section after that one, are just basically algebraic tricks that you need to use in order to use substitution. Okay, so it's all about substitution, but we need to summon things that you might not like trigonometric identities, Pythagoras theorem, or manipulations of fractions, so just like some basic, I'm quoting here, you don't see my fingers, but basic algebra. But we're done with techniques of integration. Now it's just about how do we use these advanced techniques using trig identities, geometry, or arithmetics. So let's start with trigonometric integrals. So trigonometric integrals is basically the following thing. It's all about how to use trigonometric identities in order to use substitution. So trig integrals are really just using trigonometric identities, trigonometric identities in order to do substitutions. Okay, so really the true technique here is substitution, but we need the help of our favorite trigonometric identities. So the popular ones that we're going to need in this section are, of course, the most basic one, sine squared plus cos squared is equal to 1, your favorite. The second one, not as known, but tan squared plus 1 is equal to secant squared. And by the way you get this identity is basically by using 1, and if you divide everything by cos squared of theta, you're going to get this identity again, because sine squared over cos squared, that's tan squared, cos squared over cos squared, that's 1, and 1 over cos squared is secant squared. So that second identity is not really 1. It's nothing new, you just divide by cos squared, and this is how you get it. And then the more advanced one that are going to be very useful for us. So the third one, cos squared, is 1 plus cos of 2 theta over 2. And then sine squared is 1 minus cos of 2 theta over 2. Those two identities are also called like the double angled identities. And fun fact here, fun fact if you're really, really high, if you go 3 plus 4, of course, you're going to get the identity 1, because on the left side you get cos squared plus sine squared, and on the right side, if you add everything, you're going to get 1/2 plus 1/2, which is 1. So this is kind of a fun fact to verify. But anyway, so we're going to be summoning those identities in this section or the next sections sometimes in order to get to our results. The first type of integrals that we're going to be looking at in this section are powers of sine and cosine. So the goal will be to compute indefinite integrals of the form sine to some power, so power m, times cos of some power. We're going to be using n for the power of cosine dx, where m and n are typically natural numbers, so positive whole numbers. And what I did for you is I broke these type of integrals into 3 different cases. The first case is, what if m is odd? What if the power of sine is a number that is odd? I call that case the cosine case. And the reason why I call this the cosine case, it's because you can use the substitution u equal cos of x and a combination of using the first identity to rewrite this integral only depending on cosine terms, and then of course replacing all those cosine by u and getting typically just a polynomial equation that depends on u, and then this question becomes very, very simple. So that's in the case where the power of sine is odd, you use u as cosine. It's kind of weird, okay, but it's really when m is odd, you use u to be the substitution. So again here, it's a substitution idea. Now, the other odd case is when n is odd. So if the power of cosine is odd, then if you use the substitution u equals sine of x, and again, by using the first basic trigonometric identities, you will be able to rewrite this integral depending on sine only. So of course, I call the second case the sine case. So by using the substitution u equal sine of x, you will find a way to rewrite this integral, and they will only be involving sine terms. And then by using u equals sine, you're going to get typically a polynomial function that depends with respect to u, and then basic integration will get you to the final answer. So of course, both of them could be odd. Like you could have like a function or an integral where the integrand is a bunch of power of sine and cosine, where both m and n are odd. So this is still good. So basically you can do whatever you want when both are odd, but it will be easier if you use the bigger one. So if m is the biggest odd number, using u equals sine of x is going to be easier. So if n, the power of cosine is odd, is the bigger number, then you should use u equal cosine of x. So when both are odds, it's good. And actually, as soon as one of the powers is odd, it's one of the easier scenarios. So when they're both odd, it's just super easy, and you have a bunch of ways of doing it. But it's going to be simpler if you pick the bigger one for the u substitution. But there's, of course, the harder case. So what happens if both powers of sine and cosine are even? And of course, if one of them is missing, that's considered to be power 0, which is an even case. So when both powers are even, then things are a bit trickier. You have to use the trigonometric identities 3 or 4, depending on how many powers of sine or cosine you have, in order to rewrite your integral. And typically you have to use these identities more than once until you no longer have any powers other than power 1. So you have to use these double angle identities in order to break up these even powers. So if you have a degree 2, you use it once. If you have a degree 4, you use it twice. If you have 2 degree 2, you use it for each one. So you just apply these formulas until there's no longer any powers of sine and cosine, and then you will be reducing your integral to a bunch of integrals involving cos of a multiple of theta, and that's basically a basic linear substitution that you can do directly if you remember your tricks. So the double even cases are the trickier one, but again, just by applying carefully identities 3 and or 4, you're going to be able to rewrite this and bring it down to a simpler integral. All right, let's do some examples. All right, first example. Let's integrate sine cube of x cos squared of x dx. So here we have powers of sine and cosine. The first thing you do when you have powers of sine and cosine is label the power of sine and the power of cosine by using m and n respectively. So here for sine, we have that m is equal to 3, so we have an odd. That's good. As soon as one of them is odd, we're happy. And then the power of cosine, the n is 2, so this one is even. So when one of them only is odd, you have no choice. The correct substitution is to pick the even one. So you only do this if one of them is odd. So here you have no choice. The correct substitution, because the power of sine is odd, is u equal cos of x. Then you do your normal substitution, so you just continue. So the derivative of u with respect to x is minus sine, and then you just isolate dx as usual. So this is just a regular substitution now. So dx is du over minus sine of x. So if I start my substitution, I get the integral of sine cube. So sine cube does not change for now. Cos squared now is u squared. This is my substitution. And the dx, so dx here blows up. So we had u equal cos. The dx blows up into du over minus sine of x. And this is where this is really important here, because in order to use the first identity, we need even powers of sine or cosine. So here, what happens is that the sine and the cosine, the sine cube and the sine at the denominator, they simplify. And now I can put the -1 outside. You get sine squared of x u squared du. So you see here, you're still stuck. You cannot get rid of sine squared right away. But what you do, in order to get rid of sine squared, you use the first basic trigonometric identity. We know that sine squared plus cos squared is equal to 1. So sine squared is equal to 1 minus cos squared. So you apply the first identity. You get 1 minus cos squared of x. Of course, if you're clever, you can write right away 1 minus u squared right away. I'm going to do this slowly here because it's our first example. So now that you've got rid of all your sine, your integral only depends on cos, and you can use your choice of substitution. So you get 1 minus u squared times u squared du. Before you integrate, you have to simplify. So let's just distribute the u squared inside, and you're going to get the integral of u squared minus u4 du. Now we have a nice polynomial with respect to u. U squared will become u cubed, so you get -1 u3 over 3 minus u5 over 5 plus c. So if you multiply in by -1 and you replace all the u's by cos of x, you get, let's put the first one, so minus cos cube of x over 3 plus cos 5x away. So cos 5 of x over 5 plus c. And that's it. That's all. Again here, I cannot stress enough that this method dealing with powers of sine and cosine is just how to use trigonometric identities to do a substitution. So it's really just substitution in disguise. All right, that's it for that example. Let's move to the next one. All right, next example. We want to integrate sine 5 of 5x times cos cube of 5x dx. So we have powers of sine and cosine. The first thing is, let's label our powers. So here m is 5, so which is odd, so good. Okay, so as soon as one of them is odd, we're blessed. And then your n is also odd, equal to 3. So when both are odd, that's super, super good. So when both are odd, always go for the one with the highest number. So we're going to use sine of 5x for the u substitution. So here u is going to be sine of 5x. So then you start your substitution technique. So if u is sine of 5x, then when you compute its derivative, you get 5 cos of 5x using a small chain rule. And if you isolate dx, you get that du over 5 cos 5x is your formula for dx. So we will be able to get rid of dx by replacing it by du over 5 cos 5x. So here sine of 5x turns into u. So sine 5 will be u5 cos cube. For now, we'll stay cos cube. And the dx will blow up into du over 5 cos of 5x. So if you take the coefficient outside, you get a 1 over 5. The u5 stays u5. And of course, cos cube over cos of 5x will be cos squared. Now, what you're going to do, of course, is you want to get rid of all those cosines by using the first identity here again. So we know that cos squared is going to be equal to 1 minus sine squared. So the sine squared is good. So any sine term will be very easy to replace. So that sine squared will turn into a u squared. And now the only thing you have to do is distribute this u squared inside the parenthesis. So you're going to get u5 minus u7. And now you're ready to integrate. u5 goes to, so u5 goes to u6 over 6, and u7 goes to u8 over 8, where, of course, u is going to be replaced by sine. So you're going to get 1/5 times sine 6 over 6 minus sine 8. 5x over 8, and if you multiply the 1 over 5, if you really are in the mood, your final answer can be simplified to sine 6 5x over 30 minus sine 8 5x over 40 plus c. All right, and again here, when your m or n are odd, good. Okay, so if there's only one odd, you always choose the other one for the u substitution. If both are odd, pick the biggest one. And by using the basic trigonometric identities, there's always a way to simplify this question. All right, so anyways, for that example, actually for this video, let's end with those odd cases, the easier cases. So we'll do even cases in the next video. All right, that's it. That's all. Bye-bye.